Hello, my name is Brittany Banning, and today I'm presenting my research paper slideshow on operating system challenges that affect mobile augmented reality performance. Um, Particularly motion to photon latency and how operating system scheduling, memory behavior, and thermodynamics govern the stability of AR experiences. My paper draws from operating systems theory, real time systems research, and AR system architecture. This is a summary of my abstract. The first part, which is the challenges or problems that can happen. Augmented reality seems magical. It can be magical. Um, Personally, love Pokemon Go, and it's just a lot of fun to interact with the real world in that way. Um, However, underneath that magic is a very fragile set of timing requirements. AR has to update the world in under 20 milliseconds to avoid a visible drift. That's difficult because AR is deeply multi-threaded. Every frame involves camera capture, sensor fusion, SLAM update, rendering, and display composition, and all these threads compete for CPU and memory. So these are some of the problems that can occur, and these are some of the ways that these problems can be mitigated. So my research is focused on both the problems, why they happen, and then how those problems can be dealt with. One solution is using deadline and priority aware scheduling, which basically teaches the operating system to treat AR threads differently from background tasks. Another is adaptive load shedding, which gives the system a controlled way to simplify work under pressure. And then I touch upon a couple more, but we'll get a bit more into that. Why the 20 millisecond motion to photon window? Where does this number come from? Basically, human perception. We cannot really, our brain can't really track something. So that's kind of where this number came from. And uh, we don't really have a good experience with augmented reality if it's above this window, which basically makes it like a real time, uh, there's real time behavior on mobile operating systems. This paper is one that I drew a lot of inspiration from, kind of motivated me to write my research paper because I thought it was really interesting what they were doing. So this is an image from this paper, Motion to Photon in 80 microseconds toward minimal latency for virtual and augmented reality. They introduced an algorithm that reduces lag. So the image on the left is where you can see that detachment from the image on the chessboard, and then the right is the algorithm that they made to improve that. So it's important to look at jitter in addition to latency. Once latency is under 20 milliseconds, the main villain, we could say, becomes jitter. Jitter variance between frames causes the scene to swim around, and a lot of this jitter is internal from interrupt handling, background services, binder IPC calls, C group rules. This is mostly related to Android, so looking more at Android phones. Um, Reducing jitter usually gives a bigger perceptual improvement than lowering the average latency. Here in a picture from our textbook. So I felt like we needed to have some tie-in from our course, so that's in there. Um, okay, so why deadline-aware scheduling? Default schedulers optimize fairness rather than urgency. So, for example, this is something I kind of repeat a little bit, but um, it's a kind of a key point in how schedulers are not optimized for AR systems. For example, SLAM threads can get preempted by a photo backup service. Real-time policies like EDF or RMS can fix this by giving priority to threads that are close to their deadlines. There are some concurrency challenges. As I mentioned before, AR systems run many threads at once. They constantly put shared data like spatial maps. This creates block contention, cache invalidation, and synchronization stalls. If two threads try to update the map at the same time, one has to wait, and that wait can violate the frame budget. Future mobile operating systems will need priority inheritance, lock-free data structures, and more predictable synchronization primitives. Oh, memory allocation. This is one of the biggest hidden sources of latency. The AR pipeline allocates and frees large memory buffers every frame. On mobile OSs, these allocators optimize throughput, not timing, as I constantly been saying. It's kind of same thing. But this leads to pauses and directly violates frame deadlines. So my paper recommends region-based memory pools, pre-allocation, and true zero copy DMA paths, where frames travel directly from camera to GPU accessible memory without CPU involvement. AR can cause overheating in the phone, so then the app has to be closed, or you have to like turn off your phone for a bit. So this is problematic. Um, Predictive thermal models can solve this by forecasting heat buildup using the steady rhythm of AR frames. When limits are reached, the system should gracefully reduce resolution or complexity instead of missing frame deadlines. So there's a trade-off, and there's not really an excellent solution for this yet, but just something that could could work. There are a lot of areas of research here. A couple that I initially had in my paper, but then I took out because I feel like it was maybe too many things, and just kind of looking at operating systems, but using AI, yeah, or putting things to edge servers. But I just kind of tried to hone in on four because I feel like that's plenty for now. So um, there's zero copy camera to GPU pipelines is one place that could be more research done. Um, Real-time synchronization primitives, bounded blocking, SLAM-aware schedulers that treat SLAM as the hot task, and new input-output schedulers that can prefetch large 3D models without interfering with real-time threads. Hardware and software need to work together. The fastest AR systems work well because the hardware and software are built to sync, which keeps the motion to photon delays low. Um, True real-time AR performance requires cross-layer integration. So integration between the firmware, kernel, scheduler, accelerator, and display hardware need to all share timing information. Basically, co-designing hardware and software with AI in mind. SLAM is usually the heaviest computation in the AR stack. It often runs on big CPU cores and heats the device. So giving SLAM threads guaranteed access to those cores and protected memory can prevent preemption. Large 3D maps also create input-output delays too. So prefetching and background streaming are essential. Future schedulers might need some specific rules. Um, and that's about it. So this is my conclusion. Just quite a bit longer than this, but just to summarize it and very briefly, um, AR exposes the weak points of general purpose mobile operating systems. Real-time scheduling, careful memory management, thermal prediction, and accelerator coordination all need to work together to keep motion to photon latency below 20 milliseconds. So, really thinking about smarter scheduling, thinking about memory behavior, integrating hardware and software. Um, and that's it. So that is my presentation. This was my paper, and I had a few diagrams in here. I was maybe going to explain, but I feel like they're not too hard to uh, understand in the paper. So thank you for listening to me talk today.